So I'm Henning Steinbock. I'm a graphics programmer at Threeks, a small indie studio from Hamburg, Germany. And in this talk, I'm first going to show you really quick some games I worked on, and then I'm going to talk about graphics programming aspects of them. So I'm going to talk about meshes and asset pipelines, about shaders, and a bit about performance and debugging if we have time. And just as a disclaimer, this is not really a shader programming tutorial. I'm more going to talk about all the stuff that goes around shader programming. So let's start. A game I worked on is a Wild City Rush, free-to-play mobile game with procedural levels, and the Galaxy S3 as the min-specs device back then, 2 years ago, which even back then was really, really old, so performance was critical. And we did the game together in a cooperation with Swiper, who also published the game. It's also a startup from Hamburg. And the other game I worked on that we released is a Battle Planet. It's a VR top-down shooter. It looks something like this. You play it with a VR headset, and it was released as a mobile VR game. So you put your phone into a VR headset and then put it onto your face and play a game that looks like this. And we also made an augmented reality version that was released earlier this year. And in this case also performance was super critical because you can imagine, like, VR in general is tough, and having high frame rate on mobile devices is tough, and if you combine those two, you don't have a lot of performance left. Okay, let's start with meshes and import pipeline, things I learned about that when I made Wild City. So let's start at the very beginning. Meshes are made out of vertices. I guess people are aware of that. And each of these vertices has a bunch of attributes in it. So if we write a little C# program to look at what's actually inside the Unity default cube, we can see that it has all of this data stored for like each of the vertices. So we have the position, we have normal, two UV channels, and tangents. So really quick, what do they do? The position, I guess, is obvious. It's like the position of a point of the mesh in space. And then you have the normal, which is used for directional lighting. You have UV0, which is used for textures, UV1 for light maps, and tangents are kind of a helper thing you need for normal maps to look correctly. And the question you should ask yourself when you make a game is, do I need all of them? So all of this is going to be inside all of your meshes by default in Unity. And now you should ask yourself, depending on what game you make, depending on what the game looks like, what do I need? So for example, if a game looks like this demo scene, there's no textures in this game. So there's UVs in there, they take up space, but they're useless. Also, there's no light maps and there's no tangents. So really only need these two things for this specific scene. So more than half of what I have in my meshes is useless. So what can I do? The quickest thing is in Unity you have import settings where you can select whether you want light map UVs, import tangents and normals or not. And if you don't do that, then your meshes will have roughly half the size. So if you make a 2D game, for example, without lighting, then you don't need much inside of your mesh. So if you're aware of this, you can really reduce your build size, for example. And just as an example, in Battle Planet, the game I showed you a second ago, we really only had position and UV in our meshes because we didn't have any directional lighting. And this mesh is less than half the size of what it would be with default import settings, which is good for build size, but also really helps the performance because the graphics card does not need to load a lot of stuff that it's not going to use anyways. Okay, so next thing you can do, like this is like the basic thing, set up your import settings right, but you can do more stuff because you can actually script the asset pipeline. And in general in this talk I'm going to explain everything in Unity, but most of this is applicable to all other major game engines. But for now I'm just going to explain how it works in Unity. So in Unity you have files, for example FBX files with your models inside. And you have a bunch of settings where you can, decide, for example, if you want to import normals or not. And then you have Unity's mesh importer, which is this black box that you can't really interact with. So basically, you give the settings and the mesh files to Unity, and it's going to spit out a bunch of objects that you can use in the engine, like these pretty rocks. But what you can do is you can write what's called an asset post processor. At least, again, this is how it's called in Unity. And what that basically allows you is there's good documentation about how you do it exactly, like code-wise, if you just look for asset post processor. So I'm not going to go too much into detail. But basically you have a function on preprocess model before something is imported into Unity, and you have on postprocess model, which is what's happening after something was imported. And basically on preprocess model, you can affect what settings are going to be used. So no matter what you set up in your import settings on all of the different meshes, you could hardcode that this setting has to be the same for all of the meshes in my game. And that way you save yourself from having to go, when you decide, oh, I want to have this setting on all of my meshes, you can just write this little script that is going to do it for all of your meshes. So you don't have to do it manually. And on post-process model, you basically just get the mesh that was imported and you can modify it with C# code. So you can really change everything or anything about the mesh you imported. And I'm going to give you an example of why you would want to do that. So in Wild City, we had this low poly art style. So my initial idea was we would do everything with vertex color, right? No textures in the game, everything is low poly, and we just color the different vertices in different colors. You can do that in 3D programs, and that sounded like the most performant option, because again, the game had to run on phones that were 6 years old 2 years ago. So it was quite troubling to like actually get it run. But it turns out that vertex color is a super horrible workflow for 3D artists. At least that's what they told me, and I have no idea about 3D art, so I have to believe that. So because then they would have to manually select a bunch of vertices and give them manually give them a color. And apparently that's like really bad for workflow. So what they wanted to do instead is use a low resolution texture for everything. So since we didn't really have any textures in the game, it was just, the texture just had a bunch of colors and they would map every triangle in the mesh to like one of these colors. But then again, that made me unhappy because I wanted to have the performant option where we don't have to use any textures at all. And whenever you have this conflict where this is, in general, like where artists want to do it this way because it's going to make their life better, and I, as a programmer, I'm sad about that because I have like this other solution in mind that's going to be better for me but worse for the artists. That is where you should look into modifying the asset pipeline. So these are some assets from the game, and I got them like this with a UV channel, which pointed to like points in this texture. That's how textures work in 3D games. And what I did is just, instead of reading from the texture when I, like in a shader, I just wrote a little script that would do the texture fetch on import. What that means is, when I import a mesh, it would look at the UV channel, look what color that is in the texture, and just write that into the vertex color channel of the mesh. And that way I don't have to read any textures at runtime, but instead just do what I would do in a shader before the game is even being built. And once I started to have this mindset that I can modify and pre-calculate stuff when importing into Unity, I thought about what else I could do. So for example, in the game we have this very slight color gradient as a stylistic choice. You can maybe see it a bit on the house, maybe not too good on the beamer, but everything that's close to the ground is getting a little bit darker to give the game a bit more three-dimensionality. And that's like one line of shader code, so it's really easy to implement in the shader. But once I started writing a script that would modify my meshes anyways, I just thought, hey, I can also just do this when I import meshes. So when I import a mesh and I pre-bake the vertex color, I also look at the vertice position, and if it's close to the ground, I'm gonna make it a bit darker. And the next thing, for example, I did was this snow effect, where we basically in winter wanted to have this event where the game has snow in it. And again, really easy to do in a shader. You look at the normal, you look if it faces towards the sky, and if so, you just make it white, the vertice. But that's still a bunch of operations in my shader, and instead I again did it in the importer. So I looked at the normal when I imported the mesh, and if it was facing towards the sky, I just wrote a 1 into the alpha channel of the vertex color. Because in general, this channel is not used a lot of times, so it's possible that you have this inside of all your meshes anyways, and you have like one free byte where you can basically store custom data for each mesh. So in this case, I would just store in there whether this is supposed to have snow in it or not. And then if it's winter, I make it white. Okay, so takeaways, I guess, are be aware of what's inside your mesh and get rid of anything unnecessary. Write asset post-processors because you can... because they can make your life easier. Try to pre-calculate stuff. Basically look through your shaders and see, do I really need to calculate this at runtime, or can I maybe calculate this already before the game runs? and find artist-friendly workflows, because if they are happy and have a good life, they make prettier stuff. Okay, let's talk about shaders. So in a game engine in general, at least modern game engine, you have two general concepts of shaders, which are in Unity called surface shaders and unlit shaders. And the difference is that a surface shader, you basically tell the engine the physical properties. So you tell the engine, hey, look, this object is red, but it's also kind of metallic. It has a bit of reflection, or it's smooth or rough. You tell it these information. And then the engine is going to look what lights are in the scene, for example, and it's going to decide what color to actually output. And that's why, even though I just tell Unity this object is red, it's going to make it a bit whiter in the middle, and it's going to get darker towards the bottom, because that's how light works. And for an unlit shader, you just say, look, this is the color, and that color is being outputted. And both of these have different use cases. So for example, if you make a game that has to run on super old devices, then you probably want to use unlit because it's more performant. But you can use surface shaders even on mobile games if you target somewhat modern devices. But it can still be a stylistic choice. So for example, in Battle Planet, this is what the early concepts looked like. And in the beginning, we thought, hey, nice, we're going to have realistic lighting. But then we figured out, hey, shadows on a sphere like this look kind of weird. And in general, it was kind of hard to get it right. So because we figured out, basically we thought nice realistic lighting, but we figured out nothing in our concepts has anything to do with realistic lighting. So we had to figure out our own solution. And basically what we did in the end, instead of having lighting, is we just created a little texture that looks like this, with kind of the lighting information drawn into it, and we just project that onto like everything in the game. So yeah, no lighting at all, but just this kind of fake effect that was super easy to author for artists. So yeah, they could like basically create new of these lighting textures within like a minute in Photoshop. And that made it way easier to iterate and find the right style for the game. One more thing that I started using for pretty much everything is global shader variables. This is an option to provide a piece of information to every shader and every material in the game. Normally, you go into your material and you set up some settings, but what you can do is define a setting you could call brightness or something globally, and then if any shader has a variable called brightness, it's going to be set to 0.5 or whatever value you choose. And that way you can, it's easy to do effects that affect do things that globally affect everything in your game. For example, you could do a global vector that's called player position, and then in your shaders calculate the distance you have to the player and then hide the geometry that is too far away from the player to get this Mario Galaxy haunted house effect. Or for example, if you have a bunch of TVs in a scene, you could do something like set a global texture to screen texture and then show the same kind of video in all of your TV screens throughout your level. That would be a use case. Okay, one more thing about shaders. There is a concept called shader libraries or include files, where basically if you write a game and you write your own shaders, then you most likely will write more than one shader. So in this example, I have my water shader, I have my semi-realistic foliage shader that's kind of moving in the wind, and I have an objects shader for just regular objects that don't do anything special. And each of these are lit by some kind of custom logic I have, where basically just super retro or like super old school, I look where something is pointing, and if it points towards the ground, I tint it kind of grayish. So like the most minimalistic lighting you can imagine. But still, I have the code for this in all of my shaders. And what I would want to do instead is create a CG include file, which is basically just a text file where I write my basically all my general functions into. So in this case, I have a function called apply, or a method called apply lighting, which is going to calculate how the object or like how the surface should be tinted, and then I just write include lighting .cg include in all of my shaders, and that way I don't have to have the same code in all of my shaders. And now the cool thing is, if I change something about how my lighting is supposed to work, I can just do it once, and it's going to be the same for all of the shaders. And just if you look at Battle Planet, in here we have 6 custom shaders that all of the materials are using, and but they all have the same general lighting logic to them. So, and I changed how the lighting would internally work. I completely changed all about that multiple times during the development, but I just had to do it in like one CG include file and didn't have to go through all of my shaders and change the logic. So takeaways here, I guess, are consider using unlit shaders because it can be a stylistic choice even if it's not necessary for performance. Global shader variables are fun. I use them for everything. And structure your project with CG include files to make it easier to change things later on. Okay, let's talk briefly, some minutes left, about performance and debugging. So one thing that I started using a lot is working with the compiler. So a compiler is what translates your shader code into the actual assembler, into the machine code that's running on the graphics card. And normally when you program, you don't really touch that a lot because it's like, you write your Unity program and it's going to be translated to like millions and millions of lines of like abstract weird code that you can't read. But for shaders, but because shaders are so simple, it actually makes sense to look at this stuff. So because one thing is that shaders are heavily optimized in the process. So, and the cool thing is that in Unity, when you select a shader, you can just click compile and show code. And I probably should have opened Visual Studio before starting the talk. Let's see. So this is what you would get for my foliage shader in this case. And basically it's going to give you some debug information and it's going to output you the compiled code. And even without knowing anything about assembler, it was surprising to me in the beginning that the vertex shader of this is really only like 17 lines of machine code, and the fragment shader, the thing that's executed for every pixel, is only 4 lines. So the difference to like regular CPU programming is that this is so little that you can actually like look at it and debug on the assembler level. And why would you want to do that? The main reason to do that is to avoid premature optimizations. Premature optimizations are kind of the concept where a programmer thinks this is going to make things better, but it's actually going to make things worse or like less readable. One example for that would be, instead of like writing divide by 12, a lot of people, me included, think, hey, it's going to be more performant if I just multiply by 0.083. Sounds plausible, right? You don't have to divide, you just multiply instead. But it actually turns out, if you look at the compiled code, in both cases, it's going to turn into exactly the same line of machine code, because the compiler obviously knows that it can pre-calculate this. So you think you optimize your shader, but you really just make things less readable. And one really big example for that is if statements, because it is common knowledge and a lot of shader programmers still tech artists still kind of have that mindset that you always have to avoid if and else in shaders at all costs. You will find a lot of tutorials online about how to write this without if statements. But it actually turns out, if we look at the compiled code, these 4 lines of like high-level shader code actually compile down to 2 lines of assembler. And I don't see any if or else statement in there. So the compiler actually managed to write this without if and else. And the good thing is, if we write it like this, it's still going to be readable. And if you look at all those tutorials online about how to avoid if and else, they will tell you, hey, this line of code, don't write like this is bad, write this instead. And what you can see is that it's super hard to read what's actually going on. But a lot of people use this, and I have been doing stuff like this until like a year ago. But then when you look at the compiled code, it's just like it's worse readable on the high level side, and it actually compiles to more shader code. So you really want to, sometimes when you think this is going to make my code faster or better, it makes sense to just look what changes in the assembler. And if it gets less, then it's probably better. If it gets more, then it's probably worse. And yeah, that way, by just looking a bit about what's happening, you can avoid to make things that look ugly and make your code harder to read without really helping. Okay, so takeaway, look at compiled code and don't optimize blindly. And that's it for today. Thanks.